Hi everyone, Ivo here. After a short pause, I'm back with a new video that's covering one of the latest and greatest distributed systems taking the world by storm, Apache Kafka. So I hope you enjoy it, and if you have any suggestions or comments on how to make these videos better, let me know in the comments below. Enjoy! This video is intended to be a high-level introduction to Apache Kafka. Hope you enjoy it. Let's get to it. Now, what is Apache Kafka? It's a high-throughput, low-latency message broker for real-time data feeds. It is cross-platform and it's available for all modern languages, and it has a collection of libraries for both client and server. Written in Scala and Java. A little bit of history around the system is that it was created in 2010 in LinkedIn and it was open sourced a year later. Nowadays, the company that looks after the project is called Confluent, and the name is indeed inspired by the famous author Franz Kafka. Now, what does the system offer? It offers high availability by having replayable data streams stored in a distributed fashion across an entire cluster, support for multiple availability zones across multiple geographic regions. It's very scalable. It offers infinite horizontal scalability, thousands of brokers, trillions of messages, elastic storage, and so on. But what makes Kafka stand out and why is it so popular is actually its performance. It is extremely fast. We're talking around 2 millisecond latency. It's 15 times faster than RabbitMQ, and you can technically do 2 million writes per second. There's a small caveat to achieving that performance. If you're more interested in the details, I have references to the sources of this data at the end of the slides. Of multiple topics. Each topic is a separate stream of messages. So for example, we have here topic A, B, and C. These could be, let's say, train tickets, airplane tickets, and bus tickets. For sake of example, they are intended to be consumed by different applications that have different mechanics in terms of how they process the messages. So, having this in mind, once the messages arrive in the topics, they get consumed by consumer groups. So, on a high level, this is all that happens. So let's dig in a little bit deeper. Now, the producers push the messages, and the messages get allocated to a topic based on the records key. So this is how, once the messages arrive, they get allocated to the correct topic at this moment. Then what happens is we have a pull mechanic from the consumers from the topics. Now, I'm going to touch a little bit later on the leader, in-sync replica, and so forth once we talk about the consumer mechanics in just a second, so we'll ignore it. Now, talking about the consumer groups, the important element here is that one topic can be processed by one consumer group at a time. Now, how many individual consumers you can have per group is a separate choice. So here we have 2 per group. So they don't necessarily have to be the same in all groups. It depends on the flow of messages you're going to get in each topic. However, because of this limitation, here I have presented this example where you have topic A consumed by consumer group 1 and topics B and C are handled by consumer group 2. The purpose for this is that the order of consumption of messages is guaranteed and you can consume them in the order they've arrived. On that topic, and whether the delivery is at most once, retries, and all the details we're going to cover in just a few slides later. So this is kind of the high-level overview. What you should know at this point now is that once we have the messages arrive, they are written to the leader partition for each topic, and then what you have for the other partitions is something called in-sync replica. It's essentially the same data that is synchronously replicated, and each consumer group can read for any replica. The idea there is that, for example, if a machine goes down, and now you need to start processing messages from a different set of machines. You have this topic perfectly replicated, and the failover mechanism kicks in. A new leader gets elected, it starts receiving the new messages, and your consumer group can continue consuming messages. So you have no downtime, or if any, it's minimal. Once these messages are consumed, the way the consumer groups kind of keeps track of where they're located when it comes to consuming the list of messages is something called message offset. This data is stored in Apache Zookeeper, which is also a separate distributed system on its own with multiple nodes for redundancy and so forth. It also keeps track of the broker ID that is sent to producers to know to which brokers to send their messages to. So without Apache Zookeeper in this equation, basically, the entire thing will fall apart. But Apache Zookeeper is a very well-tested, reliable system. And now Kafka using it essentially facilitates the element which is keeping in sync the updated offset and the broker IDs, so that there is no kind of double processing of messages and so forth. Now, for the consumer mechanics, we're going to talk about how the log actually works and some of the most popular jargon around it. So what we have here is 3 partitions, and we're going to focus on the first one. So the first one, as you can see, has at this moment 12 messages, and the producer is sending us an extra one, and it gets appended at the end. In this case, it's number 13. So this is the log, and what you have for a start is the last committed offset. So this is the offset that the consumer group has committed back to Kafka that these messages have been processed. Current position, which is now pointing to the 6th message, is the one that's being processed. Now, the thing is that why could these two be different? Well, if you want to do a patch application, you don't necessarily have to send that you've consumed and processed this message after each message, right? You may want to consume 5 or 10 and only after then come back to the system and say, hey, I've read these 10 messages, give me the next 10 and so forth. So if you're very real-time oriented and you definitely want to make sure that everything is as up to date, yes, it's a common use case to have immediately commit the offset after each processed message, which is probably the most use cases for Kafka, but it's not necessarily the case. This is why in this example we've had them separate. Then you have the high watermark, which is the offset of the last message that has been successfully copied to all log replicas. So we already mentioned that the replicas have the same set of messages as the leader, but because they're synchronous replication, obviously the leader gets the message first and then the replicas follow, and this high watermark identifies, okay, these copies have the messages up to this point in order for the behavior to be correct for everything else. Meaning, if you need to do a failover and you realize, hey, I'm missing messages, I need to kind of take this in mind when I do processing in XYZ. And log end offset is essentially the end of the log, which is increased as more messages come in. I hope this makes sense. It's quite straightforward. What happens is you have the oldest messages at the start, the newest one in the end. Each consumer remembers the offset they reached by using the Apache Zookeeper we mentioned earlier. Each consumer group has its own offset per partition, just because one topic can be worked on by one consumer group, as we mentioned. And the use case where you could have different last committed offset and current position is also allows you the flexibility to set custom polling time. So instead of getting every message as it comes, you can say, hey, give me the messages every 1 minute, whatever is aggregated, I want to process them then. It's very flexible depending on the use case and the system you're building. the type of data flow you have, and so forth. Now, the producer semantics. When we talk about distributed systems, it's almost inevitable not to touch the delivery type. So this is not unique to Kafka. It's unique to basically any system that deals with multiple clusters, consumers, shards, and so forth. Now, what everybody wants is exactly once. What this is that each message that gets sent is delivered once and only once. So there is no chance of you either missing it or skipping it. So think of it if you're doing banking transactions and you pay for something, you want to be charged exactly once. You can make an argument that maybe you would prefer to not be charged at all, but for the case in our example, assume we want to be billed exactly once, we don't want to be billed twice. Creating a system that achieves this is not straightforward. So right now, we're going to touch on the most popular types and what settings we have. So at most once is basically when messages are sent to the system once. If the system got them or not, we don't care. So the best case is that it processes it once. Worst case is that we never process it because the message never arrived. So you have no guarantee. And this is okay if we're talking about logs where you get tons of these, and missing one log message out of millions, it's probably okay because it's not crucial sensitive data. Now, this can be configured here by disabling retries on the producer side and committing offsets in the consumer prior to processing a batch of messages. Now, then we have the other end of the spectrum, which is at least once. Messages are never lost, but you might consume some of them twice. This is the default behavior because it guarantees that you're not losing data, and if your system is idempotent. What this means is that if you process the message one more time, the end result should be the same, right? So instead of kind of getting different result every time you get the same input, it should be the same. So the fact that you've processed it twice shouldn't actually make any difference to the end result you're getting. And this is why it's the default behavior. Obviously, this is not the case for many systems. As I mentioned, financial transactions will probably charge you twice. So this is not necessarily suitable there. And then exactly once is what we already mentioned, which is once and once only. Very, very hard to achieve because of computers going down, internet connection being unreliable. The real world is not as easy to achieve this perfect scenario when it comes to computer science. Now, options, you have strong guarantee and can miss a message. So I already touched on this a little bit. Now, the strong guarantee is that you have synchronous commits and a wait on all replicas. So what this means is that once your message arrives on the topics leader and it gets replicated to all replicas, you can either wait that it arrives on all replicas before you go forward, or you can say, hey, it's already on the leader, move on. And I know it's gonna eventually get in sync with the replicas, but I don't wanna wait this extra millisecond to kind of lose processing time. So it depends on what is more suitable for a use case. As I mentioned, if you're storing logs data, maybe this is fine. If it's something mission critical, which is usually financial applications, probably it's not. Now, consumer semantics. We have at most once, at least once, and exactly once. So very similar to what we already covered, but with a slight twist here. So the consumer reads the message, saves the offset in the log, and then processes the message. It crashes after reading and committing the offset, but not before sending the output from processing, and other consumers would move on and the message would be ignored. So this is consumer failure. I hope this makes sense. So the idea is you have basically three actions you need to do. You do the first two, and you fail on the third and you basically fail to say, hey, I'm done processing, move on. So this is what at most once consumer failure is. At least once is the consumer reads the message, processes it, and then commits the offset. It can crash after processing the message, but before committing the offset. So then what happens is a new consumer takes over this message again because it doesn't appear that the message was processed. The better choice is to have a primary key and the updates are idempotent, as we mentioned. So processing the same message should yield the same result and you shouldn't care, because the old data gets replaced with the new one, and the fact that one consumer wasn't able to commit that it processed the message successfully shouldn't matter. Exactly once, which is supported in Kafka streams, which we're going to mention a little bit later. The consumer position is stored as a message in a topic, so we can write the offset to Kafka in the same transaction as the output topics receiving the processed data. If the transaction is aborted, the consumer's position will revert to its old value, and the produced data on the output topics will not be visible to other consumers, depending on the isolation level. That is a mouthful. I encourage you to pause the presentation here to read this once again and think a little. Simply because I am perfectly aware that this is a lot of content on a slide all at once to be thrown at you. So think it through and it's going to make sense. Basically, in a nutshell, the idea is that you use the Kafka system as a way to store the offset, which gets stored in its own system. So it's a very kind of recursive, use your own system to achieve the same result. It's very clever. It does have some downsides, but we're not going to go into it. External systems. Now, a good recommendation when you deal with external systems is to do a two-phase commit between the storage of the consumer position and the storage of the consumer output. This can be handled quite simply by letting the consumer store its offset in the same place as its output. This is better because many of the output systems a consumer might want to write to will probably not support a two-phase commit. Now, let's talk about log compaction. So we're going to cover on why do we have to compact logs, how this is done, and a little bit of the internals. Now, the premise behind it is basically to restore the state after a crash. If you've lost internet connection, you have corrupted memory, and so forth. Now, another kind of good example is also to have smaller space occupied by the actual log of messages as well. Now, the way this works is there is a process with multiple threads in the background that actually compacts the messages you have, and the way it works is actually covered in this diagram on the right. So let's look at it. We have two sections called tail and head, and head is essentially the latest message for each key, and tail is the entire list of messages excluding the very last one. So the way the compaction end result looks like is this lower table where if we take, for example, key 1, you're going to see that key 1 is at message offset 2, has value 2, then value 3, and then value 4, right? So the way this gets compacted is it preserves the latest messages as they are. So the head section is copied over, but from the tail, it preserves only the latest message for each key and its value. So this is one for key 1. We have in tail message 5, which has value 3, and then value 4. So this way you have always the latest message plus the latest message for each key, excluding the very last message basically. So you get the latest two keys, latest two values per key, so to say. So this is actually the way it works. It's very simple once you see it kind of diagrammed like this. there isn't that much complexity to it. The interesting part is working asynchronously without actually impacting performance of Kafka. You can read quite a lot on the topic. There are quite a few articles on the web. Basically, the interesting piece is that as the log cleaner cleans partition segments, the segments get swapped into the log partition immediately, replacing the other segments. So this basically means is that it replaces the values in place. Otherwise, in order to do this aggregation and sorting, you would need twice the space complexity in order to achieve it. By doing this in place, you basically don't need extra space to achieve the log compaction. You need to remember that this happens for each partition, and there could be quite a few of them. Okay, moving on. Replication. So we touched a little bit on this in the original diagram, but the way it works is that each topic is split in leader and follower, right? So the leader is the main shard that takes the writes, and everything is written to, and then the followers are replicated. So here you can have 4 brokers, for example, and you have a replication factor of 2, meaning that for each shard we have 2 copies. So here, if we look at topic 1, shard 1, we see that it has a copy in broker 2 and broker 3. Then the leader in broker 2 has copies in broker 3 and 4. And as you can see through this diagram, what you achieve in the end is essentially horizontal and vertical redundancy, right? So if broker 1 falls apart, then a new leader gets elected, either in this case for broker 2 or 3, and then a new in-sync replica gets created in the following broker. So you basically have machine redundancy and broker redundancy at the same time. Kafka Streams and Kafka Connect. We're briefly just going to mention what they are. They're a separate topic. You can read on it. Kafka Streams is taking the world by storm as well because of its versatility. So what Kafka Streams is an API that allows for data transformation in real time based on Kafka messages by publishing the transformations onto a new topic. The calculations happen inside your application, not on the Kafka broker. So in other words, imagine that your messages actually contain some data, how long a person has viewed your website, and you can do real-time statistics and publish these in a separate Kafka topic. So for example, you own abc.com, and then you have people opening your website. One person is opening it for 1 minute, another for 2, and you want to have an average. Basically, this allows you to send 1.5, being the average time viewing the website, into a separate message. Now, obviously, this is for significantly more complicated examples, but it allows you to do real-time statistics. Kafka Connect is an API that allows you to define pipelines to import and export data to Kafka. So the most popular use cases for this are usually databases, something like MySQL, Postgres, and so forth. And that wraps up our presentation on Apache Kafka. So again, this is an intro. I strongly advise you, if you're interested, to read more on it. It's a very, very fascinating system. Here I've listed a few of the sources if you want to cross-check some of the numbers I've mentioned in there. And with that said, thank you for listening. This was it. Thank you for watching. I hope you've learned a little bit more about how Kafka works, if you found its design quite interesting, and you've learned a little bit more about distributed systems in general. If you have suggestions on what other technology to cover or go through, leave a comment below, and yeah, until next time, see ya.